So hopefully most of you managed to submit, or hopefully all of you managed to submit assignment 3 last night. Just as a reminder, there's sort of 6 building blocks that make up a robotics experiment that we're doing in a physics engine. We have the links themselves, the physical objects, the joints that connect those links together. The robot needs some sensors to be able to sense its world, which you just finished with. And in assignment 4, starting today, you're going to be implementing motors on your robot. Just a few notes about assignment 4. At the end of assignment 4, you're going to be implementing open loop control, which we've talked about. I think we've talked about already. Our robot has to be able to sense, think, and act, where think basically means transform sensory input plus any internal state into motor commands. A robot that simply acts on the world without detecting the sensory repercussions of that action is acting in an open loop sense. It's acting, causing a change between its relationship with itself and the environment, and then it acts again and acts again and acts again. When we get to assignment 6. When we get to assignment 6 and 7, you're going to be adding the 5th and 6th piece to your robot, which is neurons and synapses. Neurons and synapses in a neural network connect the sensors to the motors. Once you add a neural network, your robot will be capable of closed loop control. The robot will sense something, transform those signals using neurons and synapses into motor commands. The motor commands cause a change of the robot relative to its environment. The robot senses some or all of that change. There's a sensory repercussion to the action. Sensors change, neural networks change, motors change, relationship to the environment changes, sensors change, neural network changes, motor changes, and so on. So that's the distinction between open loop and closed loop control. You'll get some experience this week working on open loop control. Any questions about the assignment so far, or assignment 4 in particular? So far, so good? Okay, so let's push on with our lectures. We were talking about physical simulation last time, and we will finish up that lecture today, and that will finish up our discussion of the tools of the trade. Obviously, neural networks, evolutionary algorithms, and physical simulation, these could all be courses in their own right. So we are, by necessity, sort of just doing a crash course in these 3 tools of the trade. We will switch gears today and start in on our 3rd theme, which is the history of the field of evolutionary robotics. Okay, so back to physics engines or physical simulation. We're contrasting them against computer graphics to start off. The most important equation that you will see in this course, which is not overly complicated, Newton's second law, force equals mass times acceleration. In a physics engine, that's rearranged into acceleration equals force divided by mass. All of the objects or the links in your physics engine have various masses, and at each time step of the simulation, the physics engine applies various forces to those objects, including gravity. If links are connected by a joint and they are trying to move in opposite directions, the physics engine will apply an additional force, pushing those objects together. If the object falls and comes into contact with the ground will apply an opposing force to the object to keep it from sinking further into the ground. There are many, many other forces that come to bear on objects in a physics engine, but we're not going to talk about those. For those that are interested, there's some great online tutorials out there. Okay, we were looking, in order to illustrate the various aspects of physical simulation, I was drawing some examples from C++, and I was drawing those examples from a different physics engine called Open Dynamics Engine. We used to use that physics engine in this course. We now use PyBullet. But I think it's worthwhile to look at ODE because it's easier to get down into the engine room of ODE and see what's really going on under the hood. PyBullet, as you now know, is designed to try and hide a lot of the details from you. Okay. In ODE, links are known as bodies, but basically the same thing. They are physical objects that have mass distributed throughout the object. The object has an initial position. We talked about specifying orientation in 3 dimensions. You can do so using quaternions, but quaternions are very difficult to manipulate if you don't have a solid mathematical grounding in quaternions. So later in this course, when we start to arrange objects in 3D space, if we're working with cubes, we'll try and keep things upright, but if you need to align something along an axis, we'll use cylinders. If you use cylinders, you can get away with just 3 numbers, which specifies the 3D vector, and your cylinder should lie along that vector. We talked about hinges and hinge normals last time. And we ended last time by starting to get into contact detection and resolution. Contact detection and resolution. This is often the most trickiest, most computationally difficult part of a physics engine. It is usually the limiting factor in terms of computation. So you've already played around with adding lots of different links to your physics engine. You notice how your physics engine slows down when you were building those towers. If you take the exact same number of links and you distribute them widely, so none of them are anywhere near any other link in the physics engine, you will notice that your physics engine runs much faster. The reason why, as we talked about last time, is it takes quite a while for the physics engine to perform collision detection. Which pair of objects, if any, are in contact with one another? We'll talk about collision resolution in a moment, which is how does the physics engine resolve those collisions? How does it deal with them? Okay, the first thing we saw last time is obviously if we have, for example, 9 objects, we need to visit each of the 9 and compute whether it's in contact with any of the other 8 objects. We introduced this idea of collision spaces last time, or collision space is sort of a bounding box that you place around subsets of objects that seem to be close to one another. And by doing so, you can reduce the amount of pairwise comparisons that the physics engine needs to perform to detect collisions. How many pairs need to be considered in collision space 1 here? If you have an idea, go ahead and type it into chat. In order for the physics engine to determine whether any of the 4 objects in this space are in contact with one another, how many pairwise how many pairwise comparisons does the physics engine need to perform? Right, so Lucas has got the right equation, and M. Burak and Parker have the right numbers, 6. So Lucas has n times n minus 1 divided by 2. So we need to visit each of the n elements and compare it again, for each one of those n, compare it against n over 1, n minus 1, all the other n minus 1 objects, which is the n times n minus 1. And we can divide by 2, because if we've already compared link I to link j, we don't need to detect whether link j is in contact with link I. We already know that. Okay, so how many collision detection, given Lucas's equation here, how many pairwise comparisons do we need to perform in space 2? How do we determine whether any of the 5 objects in collision space 2 here are in contact with one another? 10, exactly. Okay, so we have a total of 16 comparisons here. Total of 16 comparisons against 36 here. We have 9 objects. 9 times 8 is 72. 72 divided by 2 is 36. There is one additional comparison we need to do here, which is whether the bounding box of space 1 and the bounding box of space 2 are colliding with one another. So we need to do a 17th comparison. What do you think we need to do if it turns out that those 2 boxes or those 2 spaces are actually colliding with one another? What happens if we detect a collision event in the 17th pairwise comparison between space 1 and space 2? So in these 17 total comparisons, we've determined yes or no whether any of these objects are in collision with one another, if any of these objects are in collision with one another, and we've just performed this 17th test, and we've determined that space 1 and space 2, these two bounding boxes, are colliding with one another. As Logan mentions, we need to determine now which pair of links will collide in space 1 with space 2. So we have to go back to the worst case where we need to do the remaining number of comparisons. So we've done 16 so far. There's 36 in total that we would need to do if we need to consider all of these. So we need to do an additional 20 comparisons in that case. If we've done our 16 comparisons and box 1 and box 2 are not in collision with one another, we're done. So you can get a sense of how this hierarchical approach works. Imagine we have a swarm of robots, and a few of the members of the swarm are quite close to one another, and some other members of the swarm are far from one another. We can use this more sophisticated collision detection algorithm to simplify the number of collisions. If we simulate a swarm of 100 robots, then we need to do 100 times 99 divided by 2 comparisons. Otherwise, that's not likely something you'll be able to do on a standard laptop. Okay, so this is just collision detection. Let's have a look at collision resolution now. So again, here's a snippet of code that's been taken from the Open Dynamics engine. In Open Dynamics engine, ODE, there is a specific C function called the near callback function. It is a callback function, meaning that this function is called whenever a certain event is happening inside the physics engine. Some of you may or may not have come across real-time programming before, or event-based programming. This is an example of that. What event triggers a callback function? A callback function is called when a pair of objects are near one another, or bounding boxes are near one another. At this point, the physics engine doesn't even know whether they're in collision with one another. So in this case, it takes the near callback function is called by the physics engine. The physics engine says geom01 and geom02. If you remember from last time our discussion, geoms are the sort of the skin that wraps around your body in a physics engine. You can think about this as the shell of the object, O1 and O2, object 1 and object 2. So if these two shells are connected, if they're connected by a joint, we'll just leave it at that. If they're connected by a joint, that's okay. They're allowed to collide with one another because they're the lower and the upper arm of a robot leg or a robot arm, and the callback function will exit early. So it's looking at these two objects. If they are not connected with a joint, then they should not be colliding. They should not be, we need to resolve the collision. So if we pass this return point, we're assuming that the two objects here, they're actually colliding with one another. And if we've just updated their position, they may not just be colliding, they may actually be interpenetrating with one another a small amount. So here we have two spheres that are slightly interpenetrated, and the arrows here represent how this collision event is going to be resolved. Forces are going to be applied to this object, pushing it this way. And this force is going to be applied to this object, pushing it this way. Okay, how does it do this? This is actually not a tricky thing. So let's switch from two spheres to two cubes. Let's imagine that we have these two cubes here. And let's imagine that this callback function has been called because these two cubes are close to one another. And let's assume that they're not just close to one another, they're actually touching. So there is some interpenetration between these cubes. In this cartoon example here, I have the two faces of the cube right up against one another. You can imagine that they've interpenetrated a small amount. There are different ways to resolve a collision. The way that Open Dynamics engine does this is to sprinkle a number of points. Actually, ODE does this and PyBullet does this as well. It detects the surface area. For example, if these two faces are touching one another, the faces have passed through one another, or in the case of the spheres here, we have this space. It computes the volume of interpenetration, the volume in which both objects are located, and it sprinkles a bunch of points inside that surface. It then labels those points with various parameters, which I'm not going to describe here, but you can notice from the name of some of these parameters, like bounce, they have to do with what kinds of forces are going to be applied when this interpenetration is detected. If we have two steel ball bearings that have come into contact with one another, these forces pushing them apart may be small in magnitude, meaning they approach one another at high velocity, they hit, and they more or less cancel out those forces. There are only small forces pushing them apart. There is still the strong force of gravity, so maybe those two objects collide and fall to the ground. Alternatively, if bounce is set very high, that might mean that we are trying to simulate two rubber balls that come into contact with one another, and now the forces pushing them apart should have high magnitude. Remember that we as the programmer do not determine those forces. We just describe physical properties of links and joints, and in this case, what happens when two links come into contact with one another. We describe that situation as best we can, and the physics engine determines what forces to apply. Okay. So when that happens in ODE, it creates joints, which sounds kind of odd. These are not hinge joints like we've talked about before, elbow and knee joints. These are contact joints that do not allow the objects to move further towards one another. Remember that hinge joints apply forces to keep objects from separating if they're attached by a joint. In a similar way, contact joints allow objects, stop objects from pushing further towards one another and increasing the volume of interpenetration. I'll just pause there for a moment. Any questions? One last detail here. In the case of hinge joints or linear joints, if we're making a piston, they last throughout the simulation. You define them at the beginning of the simulation, and they last for every time step of the simulation. Contact joints are temporary. They're created during the time step in which the objects are detected to be interpenetrating. Those contact joints apply their forces, represented by the arrows here, on these objects to slow them down or to stop them from interpenetrating further. And then those contact joints are deleted. At the next time step, if these objects or different objects are in contact with one another, the physics engine will sprinkle additional points between their volume of interpenetration. Missy has a question. Go ahead, Missy.
So in that figure, if there was one more box to the left of it that was colliding, wouldn't that kind of, if forces were applied in each direction, wouldn't that kind of make the middle box stuck? How would that work?
Yes, that's a great question. So as Missy mentions, imagine there's a third cube sitting over here to the left. In that case, there may be points that are sprinkled at the intersection between the middle cube and the left cube, which means there are forces that are applying to this middle cube that might cancel each other out. So imagine we have a stationary middle cube and a left and a right cube that are moving in and collide with that middle cube at the same time. Which forces should be applied to the left cube, the right cube, and the middle cube? If we assume that the left and the right cube have exactly the same mass, they are moving at exactly the same velocity towards the middle cube, they come into contact with the middle cube at exactly the same moment, then we know what forces should be applied to the middle cube, which is no forces at all, right? Most of the time in the physics engine, we don't have perfect symmetry like that. Maybe two objects are coming and they come into contact with the middle cube at just slightly different times. So that middle cube will vibrate back and forth as it's being hit by multiple cubes surrounding it. And you can imagine that in a lot of situations, the forces that are applied or how to compute those become very complicated very quickly. That's the reason that the physics engine computes these forces for us rather than us. You can get into situations where you have positive feedback loops. So imagine that these two cubes are moving towards the object, and there are other cubes that are pushing against those cubes. So there are stronger and stronger forces that are continuously pushing from the left towards the right and from the right towards the left, and they are compressing this middle cube. PyBullet and ODE are rigid body simulators, meaning it is assumed that all of the objects have rigid bodies or rigid shapes. They are not deformable. So if you have continuous forces that are acting on this middle cube and it's not deforming, you can get the buildup. You can get the buildup of forces where the physics engine is trying to resolve how everything should be moving, and you can get cases where the physics is unstable and you get an exploding physics engine. That's as the physics engines are becoming better, those situations of instability are becoming more and more rare. But some of you might still see some, depending on what you simulate in PyBullet. Great question, Missy. Any other questions before we carry on? No? Okay. Okay, so here's a screenshot from something that you just implemented. So most of you just finished assignment 3 and you're making use of a particular method in PyroSim called getTouchSensorValue for link, and then you provide the name of the link. This function will return -1 if that link is in contact with the ground or other objects. If it's not in contact with the ground or other objects, and it will return a 1 if it is. You'll notice if you go and have a look at this method that it's actually exploiting this contact. It's actually exploiting collision detection and resolution in PyBullet. We start by assuming that the sensor is not firing. We use an internal variable inside of PyroSim that will return a link index. So you're working with link. You're giving all of your links names, which are strings. Inside PyroSim is a dictionary that will convert a link name to an integer, which is what PyBullet actually works with. So desired link index is the integer associated with the name of the link you've supplied. Here I'm calling inside PyroSim. PyroSim is calling PyBullet, is calling the physics engine itself, and is asking to get back all the contact points. So at a given time step, if there are any objects that are in collision with one another, remember these points are sprinkled at the points of intersection. We collect back all of the collision points. We iterate through each point at a time. And if that point is a data structure that has various information in it, one piece of information stored in a collision point is which link is it going to try and apply forces to. So for this particular point, it is going to try and apply forces to link index. So that indicates that point, it indicates that this link is in contact with something, which caused the sprinkling of at least one point inside that link, in this case PT. If that link that has a contact point associated with it is equal to the link we've asked for touch information from, that means that link, which has a touch sensor inside it, has collision points associated with it, which means it's in contact with something, and we set the touch sensor to 1. So we're going to do more and more of this as we move through the course. You're going to be adding other types of sensors to your robot and simulating other kinds of motors. And in order to do so, we're going to simulate those sensors and motors by exploiting computations already performed by the physics engine. It is doing the physics for us. We're going to just dip into that physics and pull out the information we need for various sensors and motors. Make sense? Okay. Okay, so let's put this all together into a simulation loop. This is what the simulation looks like in C for ODE. You have your for loop in PyBullet, which is basically the same thing. Every pass through the loop is one moment in time, or one small span of time inside the physics engine. In ODE, it exposes a lot of the nitty-gritty details, which again are hidden in PyBullet. In ODE, it first determines all of the objects that are in contact with one another in the way that we just talked about. So we have this collision space, which contains all the objects which are in collision, which contains all the contact points, and so on. So we now know who's in contact with whom. If the simulation is not paused, we're going to step the world. This is equivalent to, step simulation or simulate step in PyBullet. This is the magic. This is where all the magic happens. So this function goes deep into the physics engine, and the physics engine determines all the forces and updates all the positions of all of the objects. You'll notice that there is an additional number here, a parameter that's passed into ODE. This is known as the simulation time step. This variable is hidden from you in PyBullet, but it is a very important variable to know about because, as the name implies, it determines how time unfolds in the physics engine. There are actually three aspects to time that you need to think about as you continue creating your simulated robots. And those three aspects of time, first of all, are the number of time steps. So some of you may have num time steps set to 1,000 or 10,000 or 100. That's how many moments in time we're going to simulate inside your world. So that determines the total amount of time that elapses in your physics engine. You also have the time.sleep function, which is how much time elapses out here in the real world between time steps. So as time unrolls here in the real world at real time, time is unrolling in your physics engine either slower or faster than real time. This takes a little bit to wrap your mind around. We have number of time steps, total amount of time of the physics engine. Between each moment in time, between each num time steps moment of time, we can pause and have some time unroll here in the real world and pause the physics engine. Why would you ever want to do that? Well, as some of you have already figured out, if you have a relatively fast laptop, things can go so fast in the physics engine that you can't even, it happens so fast you can't see what's happening. So we need to pause between time steps so the human visual system can absorb what's happening in the virtual world. Time step is how much time in seconds elapses during each time step. Remember that we have force equals mass times acceleration. So force gives us acceleration, and we're going to use acceleration to update change in position. But in order to change the position of the objects in the physics engine, we need to know how much time is elapsing during that change in position. If we have an acceleration and we have a time step of 1 second, and we apply an acceleration to an object, its new position may be very different from its original position. If we have a time step like here of 0.05 seconds, we have the same acceleration, but now we set time step to 0.05, there might be only a small change in the position of the object. So typically, or at least in the old days, you used to have to manually tune this value. PyBullet now tries to calculate this value for you automatically, so it's taken over control of this number. Why would you need to tune this number in the first place? Or why does PyBullet need to tune this number? Why not just set it to a certain value and forget about it? What happens if this value is very low or very high? What are the pros and cons of having a large time step versus the pros and cons of having a very short time step? While you're thinking about that, here's another way to think about this. If we set 10,000 time steps, and we set if we have num time steps equals to 10,000, and we set the time step to 1, we have 1 second for each of the 10,000 time steps. So we're simulating 10,000 seconds inside the simulator. We could reduce this to 0.05, and then so we've reduced it by 20 times. So we would do 20 times 10,000 time steps. We could simulate the same period of time if we set num time steps to 10,000 times 20 and used a time step of 0.5. Logan says, so this is somewhat similar to frames in animation in cartoons or videos. In essence, trying to capture movement by putting frames together. That's exactly what we're doing. So as we go from 0 to num time steps minus 1, each time step is updating the position. If we want to create a very accurate simulation, we would have many time steps and a very, very short time step, very small steps. And again, back to the metaphor of animation cartoons, we'd have a very high frame per second. And if you watch cartoons, you can obviously see that if you have high frames per second, you get a very smooth animation. If you have very large time steps and things are jumping quite a bit, you get a very jumpy animation. If you have high time steps in a physics engine, you get very inaccurate simulation. If we shoot a cannonball out of a cannon, we would expect that ball to describe a parabolic arc. If you imagine having a few time steps, but a long time step, you would get something that moves like this. If you have many time steps and a short time step, you would get a much smoother arc. Okay. So in the old days, you wanted to try and balance that, but the drawback, of course, is if you have very if you have many time steps and a very short time step, it takes a very long time to simulate, and time in your physics engine can actually run slower than it does here in real time. Some of you might have noticed that when you were building the towers. You might have noticed that if you dragged and tried to rotate the camera or move any objects in that set of towers, that the objects were falling in slow motion. So you have a physics engine that's running slower than real time. So in all physics engines, you are trying to balance very carefully accuracy versus computational effort, right? We don't want to wait until the end of the universe to see how our simulation ends, but at the same time, we want to have a simulation that is more or less realistic. Okay. So in ODE, back to ODE, it's updated the positions of all of the objects using this time step. This line throws away all the contact points. Remember that those are temporary. And then goes into the visualization part and draws all the objects in your simulator for you. In your for loop, this line, and all of this is hidden from you. And the only real thing you have is step simulation. Okay, again, for those of you that are interested in physics engines, you can dig into the details of PyBullet and Bullet underneath it to see how it accomplishes all these tasks. Okay, that's physics engines, however. We're going to now talk about simulating robots in physics engines. As we've already seen, we need to write additional code to simulate sensors and motors that don't necessarily come for free in the physics engine. So let's imagine we want to include touch sensors in our robot. We can, if we were using ODE, we can pull out the contact points from the near callback function, or as you're doing in PyBullet, we could just reach into PyBullet and grab those contact points ourselves. So to simulate touch sensors, we're making use of contact detection and resolution. Let's imagine, and you're actually going to do this later in the course, let's imagine that we wanted to add a photo sensor to our robot that detects light levels. Let's imagine that we tag one of our links, one of our objects, as being a light emitter, if we assume that we're going to drop a photosensor into the torso of this robot, we can simulate, and we assume that this object is emitting a light. We can calculate the amount of light that's arriving here by extracting the current position of object 1 from PyBullet, extracting the position of object 4 from PyBullet, calculating the Euclidean distance between these 2 points, and setting the light level inside object 1 to 1 over the Euclidean distance. So the shorter the distance between the robot and the light source, the stronger the light. And you can see that we're raising the denominator to the 2nd power. Anybody know why we're doing that? So as the robot approaches the light, the denominator, or the distance from the robot to the object, the light source, is getting smaller, which means the denominator is getting smaller, which means the amount of light is getting larger. But the amount of light detected by the light sensor is increasing quadratically with the distance to the object. Or alternatively, as if the robot is moving away from the light source, the amount of light that the robot is detecting is decreasing quadratically. Why are we raising anything to the 2nd power? Any physics students here? So this is known as the inverse square law. And you can go read about this, but it sort of makes sense. If you have a light source that's emitting light, there's a ball, and that light is obviously becoming more diffuse because it's the same amount of light around the object, but that the light at any distance from it is going to be less than at the object itself, and it actually falls off as a square, not a linear function. Okay, so by adding in that 2nd power, we're again adding something from the real world to make our simulation a little bit more realistic. So we can create different kinds of sensors, touch or light sensors, by exploiting different parts of the physics engine. Calculations that the physics engine has already performed, like collision detection and resolution, or the updating of positions of objects. Okay. All right, what about motors? Motors is what you're going to be tackling this week, but just to give you sort of a taste of how this is going to work. Again, these are examples from ODE, but it doesn't really matter for our purposes. Let's imagine that we have our quadrupedal or 4-legged robot here. We're looking at it from the side. So this is its right front leg, and this is its right back leg. Forget about its 2 left legs for now. Let's imagine we have the front leg attached to the torso. And remember that when we attach 2 objects together with a joint, even though this might look like 90 degrees, whenever we add 2 objects together with a joint, the angle between those 2 links at the first time step of the simulation is by definition 0. Let's imagine that we set a desired angle of 60 degrees. We would like the front leg to rotate outward to 60 degrees. We can, again, exploit the physics engine and get the current angle between the 2 links connected by this joint. Let's assume at this first time step of the simulation that the actual angle is 0. The desired angle is 60. So there's a big difference between what the angle is and what we would like the angle to be. We calculate that difference. We take desired angle minus actual angle, which gives us a difference in angles. And we set the hinge parameter, and in PyBullet, this is we tell the motor to apply a force proportional to this difference. So what you're going to be doing in this week's assignment is you're going to be creating a motor where you supply to that motor the difference between the current angle and some desired angle you'd like that joint to get to. And the motor is going to apply a torque, which remember is rotational force, proportional to that difference. Okay, so in our cartoon example here, let's imagine that this is time step 0, this is time step 1. So at the end of time step 0, the motor has applied a torque, a pretty strong torque because the difference is high, and that has caused the front leg to rotate forward by just 20 degrees. At time step 1, and it doesn't 20, 10, 30, doesn't matter for our examples. Let's just imagine it's 20. Let's imagine at this next time step that we still want the leg to be at 60 degrees. We haven't changed the desired angle. It's only the actual angle that has changed. So the difference, obviously, 60 minus 20 is 40. So the difference is now 40 rather than 60, which means the motor is going to apply less torque at the end of time step 1. Okay. As it does, in this example here, it's representing that the leg has rotated another 20 degrees forward. It's probably not going to be 20 this time. It's going to be a little bit less than 20 at time step 2, because it applied at time step 3. Sorry, it's time step 2, because at the end of time step 1, it applied slightly less torque. So what happens to this leg if this is t equals 0, t equals 1, t equals 2? What's going to happen as we run forward to t3, 4, 5, 6, 7, 8, 9, 10, and so on, where we keep asking the joint to get to a desired angle of 60? What can you tell me about the movement of the front leg? How is that front leg going to approach the desired angle of 60? No? So it's going to rotate, obviously, at the beginning. There's going to be a lot of torque that's applied, then a little bit less torque, and a little bit less torque, and a little bit less torque, until eventually, so the leg is going to rotate. Logan says each increment gets smaller and the applied force shrinks proportionally, right? So the leg is going to approach slowly, and less torque is going to be applied. And that's true in the cartoon example here, but remember that in a physics engine, there are additional forces that are acting on links. In this case, we're only thinking about the rotational force or torque that's being applied by the motor to this link. There is also gravity being applied to this link, right? So this link is rotating increasingly parallel to the ground. So there's more and more force of gravity pulling this leg back down again. So the amount of torque that might have to be applied here might not decrease over time. The leg might start to sag a little bit back, be pulled back by gravity, which means the difference between the desired and actual angle increases a little bit, and a little bit more force has to be applied. So as Missy mentions as well, we're trying to approach this limit. We also are ignoring the movement of the other legs and the movement of the robot as a whole. So as the robot is lurching around in its environment, there are forces or momentum that is pushing and pulling on this leg as well. So the difference between the desired and actual angle in real life is probably not going to steadily decrease in a monotonic fashion. Okay, again, this is why we let the physics engine handle the forces. It's not always obvious to know exactly what forces should be applied to do so. Okay, so Jonathan asks, so can it overshoot the angle from other forces? Exactly. So what happens if the angle of the front leg goes beyond 60, goes to 70? Maybe the robot suddenly lurches forward, which causes the leg to rotate to 70. The difference now is minus 10. So at that point, if the difference is a negative number, that means that the motor is going to apply torque in the opposite direction. Torque can be applied to rotate something clockwise or counterclockwise, doesn't really matter. So you can get a case where the front leg or an object overshoots and then comes back and starts to oscillate at slower, lower and lower amplitude around the desired angle. And that kind of vibration is probably not something that you want. Imagine an industrial robot arm that is trying to reach out and weld a car door in a factory. Imagine that it slams into the door and then pulls back a little bit, goes forward, hammers the door again, bang, 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 and eventually comes to a stop and then starts to weld. You can imagine that's very bad news for the industrial robot arm and probably for the car door as well. There is a huge branch of engineering known as control theory, which is how to do this well. So in this cartoon example, applying torque that is proportional to the difference is overly simplistic. It's not enough. It's not enough to make sure that this object approaches and then stops exactly at the desired angle, or in the case of the robot arm, at the desired extension. Inside control theory, there is a particular type of control of a motor known as PID control. For the engineers, you've probably heard this already. For the computer science students, you might not have come across PID control. You can go Google it. Again, it's beyond the scope of this course, but there's a beautiful branch of mathematics that deals with how to move things efficiently, get them where you want them to get to, which is 60, but get them there correctly, not overshooting, not taking forever to get to that limit, and so on. Okay. In robotics, typically, however, there is not a fixed desired position, because that would just mean the arm reaches out and then stops. It's usually the desired angle is also changing. So if we have a quadrupedal robot that we're looking at from the side, and we want that robot to trot, that means that all the legs should be moving together and it should be hopping from point to point. So the desired angles are going to change sinusoidally. What happens in that case? So let's have a look at this. This is the last step, as I mentioned, in the physics engine, which you're going to be tackling in assignment 6 and 7, which is adding in neurons and synapses. Let's take our very simple quadrupedal robot that we're looking at from the side. Imagine now there are two touch sensors, T1 and T2, in these two legs. In this cartoon example, the touch sensors can take on values 0 and 1. I know that in the assignment they take on values -1 and +1. To simplify this cartoon example, let's imagine that the touch sensors can take on either values 0 or 1. Let's make a very simple Breitenberg style neural network. We have two sensor neurons. The value of those neurons are going to be set at each time step to the state of the two touch sensors. At t equals 0, both feet are in contact with the ground, meaning both touch sensors are set to 1. Imagine there are two synapses that connect to one output neuron or one motor neuron. In this cartoon example, let's imagine that the value that arrives at this neuron is 60. Again, this is a cartoon example. I haven't told you what the weights of these synapses are, but to keep things simple, let's imagine there is no activation function. There is no function that is trying to squash the value at the output layer. Whatever value arrives here, we're going to treat this as the desired position of the motor. This is known as position control. In our case, position is angle, but it doesn't really matter. We have a desired position or desired angle that's now not output by us, the programmer, but output by the neural network. So this neural network says if both feet are in contact with the ground, I want motor 1 to apply forces to get the front leg to stick out at 60 degrees. As we just saw in the previous example, the motor is going to oblige by applying some torque, but at the next time step, it's probably not going to rotate the leg all the way out to 60 degrees. Maybe it only gets the leg out to 20 degrees. That action has had a sensory repercussion. We are now talking about closed loop control. The robot has sensed, it has thought, and it has acted. And that action has caused a change to its body. It's caused a change of the relationship of the body to the environment. In this case, the environment is just the ground plane. That change has been detected by the robot sensors. So T2, the front leg is no longer in contact with the ground, which means T2 is no longer firing, which means this action has caused a change to the values arriving at the input layer of the network at the next time step. I just want to take a moment to pause here because, again, this is sort of the heart of robotics. We have a neural network that is determining how to transform sensor values into motors. The physics engine handles the motors and handles the physics, which causes a change, which is handed back to the neural network. We have a change at the input layer, which means for the exact same neural network, there is probably going to be a change at the output layer. Remember that to compute a neural network, we take this value times the weight plus this value times the weight and store that as the output value. In this cartoon example here, we're going to assume that the value arriving at the output layer is minus 90. So I haven't told you what the weights are, but you can now probably figure out what's the weight of this synapse. Again, we're assuming there is no activation function here. What must be the weight of this synapse if the value of the presynaptic neuron is 1 and the value of the postsynaptic neuron is 90, and this neuron has a value of 0? What must this weight be? Exactly, minus 90, right? 1 times minus 90 plus 0 times anything else is minus 90. Okay, so we know this weight is minus 90. We can go back to this case where 1 times 90 plus 1 times something else has to be 60. So what's the weight of this second synapse? Not too overly complicated math for a Tuesday morning. Exactly. Okay, so this particular neural network with these two synaptic weights has produced this behavior. It's commanded a desired angle of 60 at this time step, giving rise to whatever torque this is. At this time step, we're now asking for a desired angle of minus 90, which is back towards the body. But the leg is extended outward by 20 degrees, so this difference is now minus 90. The desired angle minus the current angle, which is plus 20, gives a difference of minus 110. What can you tell me about the movement of the front leg at the next time step, at t equals 2? How is that leg going to move? So we have a very large negative difference between the desired and the actual angle. What do you think how is the front leg going to move at the next time step? We're going to ignore all the other forces acting on the front leg for the moment. First of all, which direction is it going to move in? It's actually not that obvious. It should swing outward more, possibly, because there is inertia and momentum in the physics engine, which we haven't talked about so far. So if you have a heavy object like this front leg, in which torque has been applied to start to accelerate it forward, if a new torque is going to be applied that tries to rotate it in the opposite direction, we have a negative difference now, which means we're going to apply torque in the clockwise direction. The leg is not immediately going to respond and start moving in the opposite direction at the next time step. It might, as it's moved forward, it might start to decelerate moving forward and start to rotate back again. But eventually it is going to start rotating clockwise and at a it's an increasingly accelerated rate, because there's a big difference between the current angle of the leg and the desired angle of the leg, which is minus 90. As this leg is doing its thing, as long as it's off the ground, even if this leg is moving, the values at the input layer are not changing. So the robot and any organism by definition cannot sense everything that's occurring in its environment. Our robot has a limited sense of its environment and its relationship to the world. So these values are going to remain at 1 and 0 as long as the front leg is off the ground, which means the desired angle is going to remain minus 90. So the motor, the neural network, is going to continuously command the motor to try and get to an angle of minus 90. Eventually the leg will start to rotate clockwise again, and as it does, it will start to rotate backwards, and eventually the front leg will come in contact with the ground again. What happens at the moment, or in the time step in which the front leg comes into contact with the ground again? So the front leg is rotated outward, but now the torque of the motor has started to rotate the leg back again. The leg comes into contact, the front leg comes into contact with the ground, and then any ideas? The moment the front leg comes into contact with the ground, we're back to this situation. Both touch sensors are firing, and so immediately during that time step in which the front leg comes into contact with the ground, the motor commands the motor neuron here, the neural network, commands the motor to apply torque in the counterclockwise direction again. So now the front leg, which has come in contact with the ground, torque is going to be applied to start to rotate it forward again. So given these two sets of synaptic weights, given this neural network, Logan asks, you may have already mentioned this, but why does the reference axis with which we measure our angle from change? So the reference axis, I'm not sure what you mean by the reference axis. We've set the joint. Let me see if I can illustrate this a little bit better. We've got our front leg here. We have created a joint here that connects the front leg link to the torso link. We have set a joint axis pointing into the screen, which means in this cartoon, the front leg is rotating in the plane of the screen here. So what we are applying are applying torques. The motor is trying to twist this, the link to rotate relative to the torso. So angle is the desired angle. In this example here, we're assuming that positive angles mean that the leg rotates counterclockwise in front of the torso, and negative angles mean that it's rotating under the body. So the reference angle, if you want, not the reference axis, is 0. 0 is the front leg pointing down. Positive numbers is the leg is rotated forward. Negative numbers is the leg is rotated inward towards the body. Okay. That's arbitrary. We could, instead of having the axis pointing into the screen, if it pointed away from the screen, that's still going to define a front leg that rotates through the vertical plane. But and you can play with this in the physics engine. That will now mean that a negative number rotates the leg outward away from the body and a positive number under the body. For our purposes, that order doesn't matter. We are going to evolve neural networks to produce forward locomotion. We don't care whether rotating forward is plus 30 and rotating backwards is minus 30 or vice versa. The neural network needs to figure all that out. In this cartoon example, we're just assuming that it's forward is positive angles and inward are negative numbers. Hopefully that answers your question, Logan. Missy, did you have a question?
Yeah, I was still a little confused by the same thing, since in the second picture, the arm has been rotated outward from the body, but the goal angle is negative. Is that because the resulting action is towards the torso?
Yep. Okay, so let's go through that again. So at the beginning of time step 1, this is time step 0. At the beginning of time step 1, torque has been applied to the joint here that has rotated the front leg 20 degrees forward. So the current angle at this joint is plus 20. The neural network knows nothing about angles. It only knows about touch values. So when the object has been rotated forward by 20 degrees, that has caused the front leg to come off the ground, causing the second touch sensor to stop firing. And that is something that the neural network sees. If the neural network has these two synaptic weights, then 1 and 0 results in a value arriving down here at minus 90. So the neural network, the output neuron of the neural network is just one number, and that number is being sent to the motor as the desired angle. And I'll just back up here. In the previous example, we as the programmer, we were setting the desired angle. We were typing it into the code. When you implement a neural network, the neural network outputs desired angles. So at this point in time, the desired angle is minus 90, which is back here. The current angle is plus 20. So the motor takes the difference between these two numbers, desired angle minus actual angle. So desired angle is minus 90 minus the current angle, which is 20. So the difference is minus 110. There is a big difference between the desired angle and the actual angle. And the motor is now going to apply a torque proportional to this difference. It's a big difference. The magnitude is high, which means a lot of torque is going to be applied. And the sign of the difference, positive or negative, determines whether the torque is going to be applied clockwise, whether the torque is going to be applied to try and rotate clockwise. A positive difference is going to cause the motor to rotate clockwise, and a negative difference is going to cause the torque to be applied to rotate the object counterclockwise. Make sense?
Yes.
Okay. Again, the question here was sort of why is clockwise plus and why is counterclockwise negative? For our purposes, it doesn't matter because we're going to let the neural network figure all this out. You'll see when we start to evolve robots, we are simply going to say, we want our robot to move to the right of the screen. Neural network, you figure out what the weights should be and what desired angles should be sent to get the robot to move in that way. At the moment, we're not there yet. We're just trying to see how neural networks and sensors and motors fit together. Values from the sensors arrive at the input layer of the network, and values arriving at the output layer of the neural network. These values are sent to motors, and the motors interpret those numbers as desired angles. The motors take those desired angles, detect actual angle, take the difference, and apply torques proportional to those differences. Okay, I get that this can be a little confusing because we're now sort of pulling everything together. So might be worthwhile to go back and watch this part of the video lecture later today. You can actually sit down with pen and paper and work out some of these examples yourself. You could take this slide and instead of minus 90 and plus 150, just write cross out these two numbers and write in your own randomly chosen numbers. And then go through the same exercise. If 1 times your new weight plus 1 times your new weight is going to give you a number different from 60. If the number here is a negative number, then the torque applied by the motor at the beginning of the simulation is going to try and pull the leg inward rather than rotate it outward. By changing these numbers with pen and paper, you can actually work through the first couple of time steps of our cartoon robot here and figure out how the robot will move. Changing the neural network changes the behavior of the robot. Determining what these numbers should be by hand to get a robot that walks to the right of the screen is next to impossible. In the same way that it was almost impossible for us to come up with synaptic weights to compute the XOR function. It's very difficult to do that by hand. In assignments 8 and 9, you're going to be applying an evolutionary algorithm that tries to find good numbers here to get the robot to do what you want it to do. Okay. So I want to just go back to the example we were talking about here. At time step 0, counterclockwise torque is applied, causing the leg to rotate counterclockwise a little bit, pulls the leg off the ground, which means the difference is negative. So clockwise torque is now going to be applied by the motor, which is going to start to pull this leg back down into contact with the ground. The moment the leg comes into contact with the ground, these values become 1 again. Counterclockwise torque is going to be applied. The leg's going to come off the ground. Clockwise torque is going to be applied to bring the leg back down into contact with the ground. And if you simulate this cartoon forward in your head, you're going to get a front leg that is oscillating back and forth. It's going to rotate up, back down to the ground, up, back down, and so forth. If you look at this neural network, there is no sinusoidal, there's no sine function in here. There is no evidence of an oscillation in the neural network. The oscillation emerges from closed loop control. The way the robot moves is a function of its body, how it's put together, and its brain, its neural network. This is the underpinning of embodied cognition, which we talked about 2 weeks ago now. We can get sophisticated behavior, or in this case, just simply oscillatory behavior, with a neural network that doesn't even have an oscillation in it. We have a relatively simple neural network. If what we wanted the robot to do was just oscillate its front leg, we can create a pretty simple neural network to do that. Okay. Any other questions about this before we move on? This is our last slide in this lecture series. Okay. Digest that. If you have more questions about this, come on back and ask on Thursday. It's very important that you're all able to understand how sensors, neural networks, motors, and the physics engine fit together. Okay. All right, we have just 7 minutes left, so I will just start in on lecture series 7 here, which is the beginning of our discussion of the history of evolutionary robotics. The experiments we're going to talk about now, these are from the mid-90s. So unlike calculus, which is 300 years old, evolutionary robotics is very, very new. It's only about 25 years old. So our history is actually going to be pretty short. We have 6 lectures in this section. Okay. In this lecture, we're going to talk about 2 different experiments. One that was done by Italian researchers. The second one was performed by English researchers. So we're going to talk about the Italian approach first, from our Italian researchers, and then we'll talk about the English approach by our English researchers. Like many things in the history of science, these two experiments were reported at about the same time. So both of them are sort of the first experiments in evolutionary robotics. Which one was first? As you can imagine, people in the field argue about which one, but for our purposes, these are the two founding experiments in evolutionary robotics. Okay, first one was carried out in 1996 by Francesco Mondada, who's Italian, just to make things a little bit, is Italian, but was carried out in Switzerland, just to make things a little more confusing for you. Okay, Professor Mondada used the Kepra Robot, which you see here. It's got a diameter of 55 millimeters, so it's basically a hockey puck. There's a link to a YouTube video here. You can see the latest version of this robot, the Kepra 4. It's not a very well-known robot, but it's been around for 25 years now. It's used quite a bit in academia for performing robotics experiments because, again, it's very small and you can carry out experiments very safely on the top of a table. Very simple. Okay. The other nice thing about the Kepra robot is the hardware is designed in a modular fashion, so you can snap extension modules onto the top of the Kepra. You'll notice the base has two wheels here, so it's very simple to simulate. A Breitenberg vehicle. You've got two wheels. You can snap on various kinds of sensors. You can see here they've snapped on a gripper. So this is sort of this gripper that rotates up and down. It can close the pincers of the gripper. You can see here it's grasped a sugar cube and lifted it up. Okay, we're going to look at an experiment in a moment where it did not have the gripper, but instead they snapped on a linear vision module. So very, very simple eyes for the robot. Inside this vision module, there are 36 photoreceptors that are pointed outward. So you have 36 of them, and 64. Each of these 64 photoreceptors is returning a single number, which is the amount of light that is falling on that photoreceptor. So if we took the robot and we put it up against a white wall that had a black stripe down the middle of the wall, and that black stripe was in the center of the vision of the robot, you could visualize what the robot would be seeing at that point. Most of the 64 photoreceptors arranged along the horizontal axis here are reporting very high light levels. They're pointed at the white wall, but a few of the photoreceptors in the center, which are pointing towards the black stripe, are reporting lower light levels. So this is not a camera, it's not a pixel array. We're getting a one-dimensional array of light levels. That's it. Okay, so a Breitenberg vehicle has two photoreceptors and two wheels. This is 64 photoreceptors and two wheels. Okay. This was arguably the very first evolutionary robotics experiment performed. No physics engine. This is in the mid-90s. Physics engines hadn't been invented yet. So they had to do all evolution on the physical robot. They took their Kepra and they put it on top of a table. They tethered the robot to a computer. The computer is going to run an evolutionary algorithm, which is going to try and find the weights that connect the 64 photoreceptors to the two wheels, to the two motors. So if we have 64 photoreceptors, and each of those 64 photoreceptors sends out a synapse that sends out two synapses that attach to two wheels, we have 64 times 2 equals 128 synaptic weights. By tuning the strength of those weights, we can alter how the wheels rotate in response to different values at the 64 photoreceptors. We're going to use an evolutionary algorithm, or they used an evolutionary algorithm running on the computer. to figure out what those 128 weights should be. Remember our discussion about evolutionary algorithms where we can encode all of our genes in a vector. Imagine a vector with 128 values, which represent the 128 synaptic weights. Okay. Our robot is going to do the behaving here. It's going to move around. They placed a laser emitting device in the upper corner of the box, which sent out lasers onto the tabletop. The robot had just enough computation on board to recognize the lasers, and based on which laser it detected and the strength of that laser, the robot was able to determine its current position, X and Y on the table, and alpha, its orientation on the table. We've reached the end of our time, so I want you to think how could you evolve the robot to do something on the table if you know the position of the robot at each point in time and its orientation, and you're evolving how the motors respond to light levels. Think on that. We'll come back to this on Thursday. You have a quiz due tonight, and you are now working on assignment 4. Have a good rest of your day, everyone. Bye-bye.